In today's video, we will look at taking the derivative of exponential functions and logarithmic functions. Let's start with the natural exponential function. That is, we're going to start by looking at the derivative of e to the x. And we can rewrite e to the x plus h using laws of exponents as e to the x times e to the h. We are then able to go ahead and factor out an e to the x. Now, since e to the x is constant with respect to h, we can just go ahead and factor it out of the limit altogether. Now we just have to examine this limit. The easiest way to examine this limit is to go ahead and look at its graph. So bring up Mathematica. We want to plot the function e to the x, forgot my parentheses, minus 1 all over x. And since we're approaching 0, let's take a domain close to 0, so let's say negative 2 to 2. Let's see what that gives us. So here we have it. This is e to the h minus 1 over h. And as we approach 0, the limit is 1. Right, and this is more easily confirmed by using the limit command. And there you see, it gives us 1. So since that one was 1, we're left with e to the x times 1. And that is e to the x. So therefore, the derivative of e to the x is just e to the x. We will now look at the natural logarithm function. Now, recall from pre-calculus that we said y is equal to the natural log of x if and only if x was equal e to the y. So, what we say is d dx of y is equal to d dx of the natural log of x if and only if d dx of x is equal to d dx of e to the y. Well, working with this piece, we find that equation gives us 1 equals e to the y times dy dx by the chain rule. We want to solve for dy dx. So we get 1 over e to the y. But y is log of x. So this becomes e to the log x. And that is 1 over x. Thus, we conclude that the derivative of the natural log of x is equal to 1 over x. Now that we've looked at the natural exponential and natural logarithm function, we're going to turn to the more general exponential. So remember that the base e is the natural base. It is the most commonly used base in mathematics. However, it's not the only base that can be used. We now want to look at d dx of b to the x, right? Where b is greater than 0 and not equal to 1. Well, let's rewrite this as the derivative of e to the natural log of b to the x. Then what we have is we can write this as e to the x times the natural log of b. And now we can go ahead and take its derivative. Well, the derivative of e to the x is e to the x, right? So we're going to have e to the x times natural log of b. Then the chain rule dictates we have to take the derivative of x times log of b. Now, since log of b is going to be a constant, the derivative of x times log of b is just log of b. However, e to the x log of b was b to the x. So, the derivative of b to the x is equal to b to the x times the log of b. Obviously, b greater than 0 and not equal to 1. Let's now take a look at the derivative of log base b of x. Again, b greater than 0, but not equal to 1. We're going to use change of base formula here. So we can write log base b of x as the natural log of x over the natural log of b. Now we can use constant multiple rule to write this as 1 over the natural log of b times the derivative of the natural log of x. So this is 1 over the natural log of b times 1 over x. So we therefore conclude that the derivative of the general logarithm base b, 1 over x times natural log of b, for b larger than 0, but not equal to 1. And as always, we will bring this video to a close by looking at several examples. First, let's consider the function f of x equals e to the x squared over x. F prime of x, this is a quotient rule, so denominator times the derivative of the numerator. This is going to be a chain rule, e to the x squared times the derivative of x squared minus numerator times the derivative of the denominator over denominator squared. Now we just have to simplify this. 2x squared e to the x squared minus e to the x squared all over x squared. And if we want, we can write this as e to the x squared over x squared times 2x squared minus 1. For our next example, let's go ahead and consider the function f of x equals natural log square root 5x minus 7. Derivative of natural log, 1 over the square root of 5x minus 7. Chain rule then says take the derivative of the square root of 5x minus 7, 1/2 times 5x minus 7 to the minus 1/2. Now we have to apply chain rule again and take the derivative of 5x minus 7. So when all is said and done, simplifying, we'll get 5 over 2 times 5x minus 7. Now, let's consider the function f of x is equal 3 to the x over 3 to the x plus 2. Overall, this is a quotient rule. Denominator times the derivative of the numerator, which is 3 to the x times log 3, minus the numerator times the derivative of the denominator, which is again 3 to the x log 3 over the denominator squared. We're going to wind up with 3 to the 2x log 3 plus 2 times 3 to the x log 3 minus 3 to the 2x log 3. As we can see, those terms will wind up dropping out. We'll be left with 2 times 3 to the x log 3 over 3 to the x plus 2 squared. Now we can keep going if we want. Let's write this instead as 3 to the x times 2 log 3. Well, now using properties of logarithms, we can write this as 3 to the x log 9 over 3 to the x plus 2 squared. Now, let's consider the function f of x equals log base 7 of 6x to the 4th plus 3 to the 5th power. What we should do here first is try and simplify this as much as possible. Write this as 5 log base 7 of 6x to the 4th plus 3 using the laws of logarithms. If you can simplify your logarithm as much as possible before taking its derivative, generally speaking, it'll be algebraically simpler. I leave it to the viewer to not do the simplification and just take this derivative and verify you will get the exact same answer. Now if we look at f prime, we're going to have 5 times now the derivative of log base 7. So it should be 1 over 6x to the 4th plus 3 times natural log of 7. Now chain rule, we have to take the derivative of that inner function, 24x cubed. 5 times 24 is 120. We'll have 120x cubed over 6x to the 4th plus 3 times natural log. of 7. And for our final example, let's consider the function 2 to the x log base 3 of 7 to the x squared minus 4. Now, in this case, it would not be simpler to pull this exponent down. Then we're going to have a triple product rule. Let's just leave this as single product. First function times the derivative of the second function. Now we have to do chain rule. Now we have to do chain rule again. So there we have our complete first term. Plus the second function times the derivative of the first. Now let's just go ahead and simplify this. We will have 2x times 2 to the x times 7 to the x squared minus 4 times natural log of 7 all over 7 to the x squared minus 4 log of 3 plus 2 to the x natural log of 2 times log base 3 of 7 to the x squared minus 4. So those 7 to the x squared minus 4s will wind up dropping out. We can also simplify this 2x times 2 to the x. If we write this as x times 2 to the x, we can use properties of exponents to write this as 2 to the x plus 1 x natural log of 7 all over the natural log of 3, then plus 2 to the x natural log of 2 times log base 3 of 7 to the x squared minus 4. And let's just leave it like that. Okay, so that will bring this video to an end. In the next video, we will look at taking the derivative of trigonometric functions.